Welcome back, everyone, to another deep dive.
Glad to be back.
Today, we're taking a listener request and plunging headfirst into the world of number sequences. Specifically, we're looking at entry A00018 from the Online Encyclopedia of Integer Sequences.
Oh, that's a good one.
Yeah, it's a fascinating sequence, and I think it's going to be a great deep dive for us. Now, I know what you're thinking. Number sequences. Sounds a little dry, doesn't it?
Maybe a little bit at first.
But bear with us, folks, because this one is packed with hidden patterns and connections that might just blow your mind. Now, before we get into the nitty-gritty, let's set the stage a bit. For those unfamiliar with the OEIS, well, it's a treasure trove of integer sequences, meticulously cataloged and analyzed by mathematicians from around the globe. It's a bit like a Wikipedia for number nerds, and let me tell you, there are some seriously dedicated number nerds out there.
Oh, yeah.
Now, entry A00018 might look like a jumble of numbers at first glance, but it's defined by a specific formula.
Oh, yeah, that formula.
Here it is. Number of positive integers equals 2n in a form by 2 plus 16y2. Now, I'm not going to lie, that formula makes even my head spin a little bit, so I'm really hoping you can help us break this down into something a little less, well, cryptic.
Absolutely, I think I can. Imagine you're on a treasure hunt, but instead of searching for gold or jewels, you're looking for specific types of numbers.
Interesting.
Your hunting ground is this vast landscape of numbers, and it's constantly expanding, doubling in size with every step you take.
Okay.
That's what the 2n part of the formula represents. It's a set of numbers that grows exponentially, like, think of a sheet of paper that you fold in half and then in half again and again. Each time you fold it, the number of layers doubles.
Got it.
So with each step or fold, the number of integers we're considering gets much, much larger. But we're not interested in all the numbers. We're looking for specific gems, and that's where the second part of the formula comes in. By 2 plus 16y2. Think of this as your treasure map. It guides you to the precise locations of these precious numbers within this vast, ever-expanding numerical landscape.
Okay, so we've got this ever-expanding field of numbers and a map that tells us which ones we're looking for. But why powers of 2? It feels a bit like we've wandered into a computer science class.
Well, you're not wrong to make that connection. Powers of 2 are absolutely fundamental in computing. Think about bits and bytes, the basic units of information in the digital world. Every time you add a bit, you double the number of possible values you can represent. So you see, there might be some very deep connections between this seemingly abstract sequence and the very foundations of computer science.
Okay, now that's really interesting. So we've got this treasure map, we've got this exponentially growing field of numbers, we've got potential links to computer science. What about the actual treasures? What do the first few numbers in this sequence look like?
Well, let's take a look. The sequence starts with 1, 1, 2, 2, 4, 8, 13, 25, and so on. It doesn't increase in a simple, predictable way, does it? It jumps around a lot.
It does, yeah.
But it's definitely not random. The numbers are growing, but the rate of growth is kind of erratic. I think this unpredictable behavior has something to do with the interplay of squares in the formula, those by 2 and 16y2 terms, and the fact that our hunting ground is doubling in size with each step. And here's something that I find really intriguing. Prime numbers keep popping up in this sequence, like the number 13, for example. Prime numbers, remember, are those special numbers that can only be divided by 1 and themselves. They're the building blocks of all other numbers. And their appearance here hints at some deeper connection to the fundamental structure of numbers themselves.
Yeah, it's like this seemingly simple formula is a window into some sort of hidden structure within the world of numbers. It reminds me a bit of those fractals, those infinitely complex patterns that arise from relatively simple mathematical equations. Now, speaking of deeper connections, in my research for this deep dive, I came across a paper by D. Shanks and L.P. Schmidt titled Variations on a Theorem of Landau that references this very sequence. Are you familiar with that?
Oh, absolutely. Landau's theorem is a big deal in number theory. It deals with the distribution of prime numbers, how often they appear as numbers get larger and larger. The fact that our sequence is connected to Landau's theorem suggests that it's not just a mathematical curiosity. It might actually be a tool for understanding how prime numbers, those building blocks, are sprinkled throughout the vast universe of numbers.
So we've got this unassuming formula that generates a sequence with links to prime numbers, computer science, and a major theorem in number theory. That's a pretty impressive haul for one little sequence, I think.
It really is. For me, the biggest takeaway is that a single, seemingly arbitrary formula can unlock so much about the structure of numbers. It's like a tiny key that opens up a whole universe of mathematical connections and possibilities.
It really makes you wonder, What other mathematical secrets are hiding in plain sight, just waiting for the right formula to unlock them? So to our listeners, I say this: keep exploring, keep questioning, keep digging into those numerical rabbit holes. You never know what fascinating treasures you might find. Thanks for joining us on this deep dive.
It was great being here.